All right, so we've dealt with an informal definition of a limit and seen how we can find it graphically as well as numerically. We've also seen where a limit does not exist. And now we're going to move on to the formal very mathy definition of a limit. Okay, so don't get too freaked out. Hang in there and we'll be all right. So our informal description, which might be mathy enough for you, was if f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. So that's exactly what we've been dealing with. Now let's kind of break this down and see what this means. So this first part here, f of x becomes arbitrarily close to a single number, means that f of x lies in the interval L minus some epsilon, comma, L plus some number epsilon. Here's what that looks like. Let's just draw a straight line as our function. Why not? And we'll choose this point right here as our limit. Okay, so again, this is the point C, comma, L. We can see where this maps onto the x-axis, then onto the y-axis, and we get L here. Okay, so this first part, if it lies in the interval L minus epsilon and L plus epsilon, that's basically talking about a distance where our f of x is going to be within epsilon units of the limit. Okay, and we do that with an absolute value sign. So absolute value, when we're dealing with that, all we're talking about is the distance of epsilon. We're going to call this arbitrary number L plus epsilon. We're going to call this number L minus epsilon. Okay, so what that means is this length right here is epsilon. Above it and below it, and it gives us these 2 points, L minus and L plus epsilon. Okay, and that's what it means to say f of x becomes arbitrarily close to a single number. It means it's somewhere in between here. And that's all we're talking about. Now, the x approaches c portion means there exists a positive number, we'll call this delta, such that x lies in the interval c minus delta, comma c, or c, comma c plus delta. At any rate, we're going to have x minus c being between 0 and delta. So all we mean by that is we're going to take delta away from c. We'll call this c minus delta. So there exists a delta where we can subtract it there, and also where we can add it. Okay, so you can see x is approaching c, meaning we can get somewhere close enough within delta of c such that this happens as we map c minus delta up to our function, and if we map it back over to the y-axis, it's going to give us an f of x that falls within this range. Likewise, if we map c plus delta, so delta above c, up to our function, and then we map it back over to the y-axis, that value of f of x will also fall in that range. Okay, so basically we're saying as we look at getting closer and closer to a specific number, our L, which is an f of x, there's a certain number delta that if we're within close enough to c, it's going to give us an f of x that's somewhere in that arbitrarily close range. Okay, thoroughly confused? Maybe. But anyway, this is the formal definition, and we're going to talk about how we can use this now to prove that a limit exists. Okay, so it's going to be very important that you memorize this formal definition, also called epsilon delta definition. So if you see that this is what we're talking about. So the limit as x approaches c of our function f of x equals L means that for each epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c is between 0 and delta, then f of x minus L, the absolute value, is going to be less than the epsilon. Okay, so whether you understand this definition or not, we're going to use it right down here in a couple examples and see how this works. Okay, so it says given the limit as x approaches 3 of our function 2x minus 5 equals 1, so they're giving us the limit, they're saying the limit is 1, find a delta such that the absolute value of 2x minus 5 minus 1 is less than 0.01 whenever the absolute value of x minus 3 is between 0 and delta. Now again, this may not mean a whole lot to you, but you need to be able to identify the different items in this from the definition. Okay, if we can do that, we'll be on a good start here. So as I look at all of this, I'm seeing the limit as x approaches 3. Well, what is 3? That is our c value. So we know that c equals 3. If we look right in here, this is our f of x. So we also know f of x equals 2x minus 5. And we're saying the limit equals 1. So 1 right here is our L. L equals 1. Now they're asking us to find a specific delta such that all of this is true when this is true. So in this first part, let's see if we can identify this as to where it fits in with our definition. And a lot of times when you do this, you're going to see this backwards. So just kind of look here. You're going to see that this left side is the right side of our definition. So we start backwards. So you can see here's your f of x, right? Which is the same here. And then minus L, you can see that there. Minus L is minus 1. And then less than. And this is less than epsilon, and here we have 0.01. So for this example, we're going to let our epsilon equal 0.01. Now, this is going to be whenever the absolute value of x minus 3. Okay, now what is x minus 3? Well, this section looks exactly the same as this one. So x minus c is between 0 and delta. So now x minus 3 is between 0 and delta. So you can see our letter c is right there. Okay, so hopefully you can understand where all the pieces of this puzzle come from. So graphically, let's see what we're trying to do here. So we're looking for our limit at x equals 3. So that's our c value. And it's saying the limit is 1. And we're going to prove that, pardon my stretching of the range here, but we're going to put our L plus epsilon right here, which would be 1.01, and our L minus epsilon here, which is 0.99. So our task is to find a delta so that when we map it up to our function, it gives us an f of x that's going to be in this range. So as we go delta below c, f of x is still going to be greater than 0.99. And as we go delta above c, it's going to give us an f of x that's going to be also less than 1.01. Okay, so this is what our task is, to find that delta. So here's how we're going to do it. What we have to do is get this portion of the equation to match this portion right here. So we have to get the absolute value of f of x minus L to equal the absolute value of x minus c. That's our first step in doing this. Okay, so here we go. Now comes the math. So 2x minus 5 minus 1 equals 2x minus 6. That's still the absolute value, and it's still less than our epsilon 0.01. Now, with absolute value, we can factor out our constant of 2. We're left with 2 times the absolute value of x minus 3 is less than 0.01. Now, hopefully, at this point, you can see that the x minus 3 and the x minus 3 and the absolute value are the same. Okay, so that's what we want to do. Now we want to just go ahead and get the absolute value of x minus 3 by itself by dividing by 2. So we're going to say x minus 3 absolute value is less than 0.005. So that's 0.01 divided by 2. Now looking at this, okay, if we compare it right here, that is the same. Okay, do you see that? So what we've found here is that delta is going to be equal to 0.005. So that was our task, find a delta such that this was true, and we did that. Now unfortunately, we can't stop there. We have to actually verify that this works. So to be able to do that, we're just going to rewrite this second part, okay, which is actually the first part of our definition, using the delta that we chose. So we're just going to go 0 is less than the absolute value of x minus 3 is less than our delta of 0.005. Okay, so you just want to substitute that right into the second part. Now this implies, and this is going to feel where we're just going backwards. We're almost restating exactly the same thing. So this implies, and we're going to rewrite this part, f of x minus L. So 2x minus 5 minus 1. And then we're going to equate it to, well, everything that we did over here. So it's 2 times the absolute value of x minus 3. And we're going to say that's less than 2 times our 0.005. Okay, so we're just kind of undoing everything we did here. So we're going backwards. We're going to say that equals 0.01. And so here we ended with the exact same thing we began with, the epsilon of 0.01, and that's how you're going to show that this delta of 0.005 actually works. And so what that tells me here is if I pick a C value of 3.005, or if we go 0.005 below, which would be 2.995, it's going to yield my L value, or f of x value, that's between 0.99 and 1.01. Okay, so in doing this, we were asked to find the delta given a specific epsilon. Very important that this doesn't prove a limit exists. Okay, for us to prove that a limit exists, we're going to have to show that it works for any e, not just the one that they give us. Okay, because, you know, if we choose this e, well, maybe if we got a little closer, this whole process wouldn't work. So what we're going to try to do now is prove this for any e. So when we're trying to prove it, your example is going to look like this. It's going to say use the epsilon delta definition to prove that the limit as x goes to 2 of the function 3x minus 2 equals 4. So we're going to prove here that the limit equals 4. So again, just a couple things. Go ahead and find your C, your f of x, and your L. So I get C equals 2, f of x is 3x minus 2, and L equals 4. And let's begin our proof. So we're just going to start by writing for each epsilon greater than 0, because we're doing it for all of them, there exists a delta greater than 0 such that, we'll abbreviate that ST, such that, and what we want to do here is go ahead and start with our definition, but start with the second half of the definition. Okay, so we're going to write f of x minus L in absolute value is less than epsilon. And we're going to plug in everything we know. Okay, so the absolute value of f of x, which is 3x minus 2, okay, minus L, which is 4, is going to be less than epsilon. We're just going to leave that epsilon to represent anything. Okay, now this becomes very similar to what we did in the previous example. We want to go ahead and get this whole part to look like, well, what are we trying to get it to look like? Well, when 0 is less than the absolute value of x minus c, so we're just going to take this whole second part, okay, right from here. So we have x minus c, and c in this case is 2, is less than our delta. So what we're going to do now is go ahead and figure out what delta is in terms of epsilon. So we're going to try to get this absolute value to look exactly like this absolute value right here. Okay, so this becomes 3x minus 6 less than epsilon. We can factor out the 3. And then divide the 3 to the other side. So we get the absolute value of x minus 2 is less than epsilon over 3. Now again, because these two things match, okay, we can say that x minus 2 is less than delta, and so we can equate delta equals epsilon over 3. Okay, now that was just our first step in finding our delta. Now we're actually going to prove that it works for each epsilon greater than 0. So this is where we just rewrite this statement replacing our delta. Okay. So we write 0 is less than the absolute value of x minus 2. It's less than, replace our delta with epsilon over 3. And now we kind of work in reverse. Okay, so at this point, we're going to rewrite our original part here. Absolute value of 3x minus 2 minus 4. And again, we already know this equals 3 times the absolute value of x minus 2. And this is less than 3 times epsilon over 3, which just equals epsilon. So what we've done here is we found delta is epsilon over 3. When we plug it back in here, epsilon over 3 for delta, okay, we end up being left with just epsilon. So for any epsilon greater than 0, if this is our delta, we know we're going to get back epsilon. And so it's going to work. So graphically, let's see what that looks like. So here's c equals 2. Here was our limit of 4. Here was our 4 plus our epsilon. Here's our 4 minus epsilon. And we found that 2 minus our delta and 2 plus our delta are going to yield y values in that range of epsilon no matter where we go. All right, nice job hanging in there. And that is the end of our notes on section 1.2. Thanks for watching.